And finally, we arrive on question 1, which I think is the hardest problem. Alright, you're given the masses and an applied force this way of 100 newtons. The most important thing is that you have to check if it slips or not. If there is slippage between M2 and M1, then we need to use the kinetic friction. If M2 and M1 do not slip and they accelerate together, then we need to use static friction. Okay, but you don't know what that is given the question of the applied force. So first, we check static friction using Fs and Fs max. We draw the free body diagram to the two systems. I made sure to draw it close, but I don't want you guys to get confused. This is the free body diagram of M2, normal force and gravity, friction force acting backwards and the applied force acting leftwards or forwards. Now the two red forces on M2, okay, those two forces are coming from M1. M1 provides the forces. M1 provides the normal force which supports M2 so it doesn't fall. And M1 is also providing the friction force. So whatever these magnitudes are on M2, equal and opposite forces act on M1 according to Newton's third law. Okay? So this is key. This friction force forwards from M2 and M1, that interaction, is what gives M1 its net force forwards and causes it to accelerate forwards. And also we remember that M1 is sitting on a frictionless surface, so it doesn't have its own friction acting against it. So sum of forces in the y, that shouldn't be too complicated. We should get that n is equal to mg here. Sum of forces in the x for M2, we get 100 minus Fs max, which is equal to 100 minus 0.6, which is given as mu s, and n, which is equal to mg, so that's 10 times 9.81, which is equal to 41.2 newtons. Okay? So the acceleration in the x direction, ax, is going to be equal to 4.12 meters per second squared. Alright, this is assuming Fs max and the sum of forces divided by the mass. Okay? We found what this value is. Alright? This value is 58.8 newtons. That's important because that 58.8 newtons is coming from here and acts in the opposite direction here, which is 58.8 newtons. Alright, the normal force from supporting M2, this is N2 on 1, and this is N1 on 2, is also here, but we don't really care about the sum of forces in the y direction because we only care about the x acceleration of M1. So yes, these equations would be needed if you actually write it on, but for the x direction, all we have is sum of forces in the x is equal to Fs max, which is equal to 58.8 newtons, and we got that from there. Okay? So the acceleration for M1, in the bottom mass, is going to be 58.8 divided by the mass, which is 1.47 meters per second squared. So here, we see that the acceleration of the top block is a lot more than the acceleration of the bottom block. So the two blocks are not moving together, and there is actually slippage occurring. So I have here two blocks on the table that might help you demonstrate this. Consider this as the bottom block, no friction. Consider this as the top block with friction, and it's being pulled. If Fs max was enough for these two to have the same acceleration, then they would accelerate together like so. And you would remain in static friction, okay? You're accelerating together, the acceleration of the top and bottom is the same, and the only force acting on the bottom block is Fs max. But Fs max is not enough to accelerate the bottom block to match the acceleration of the top block. You're about 3 meters per second short. So what's actually going to happen in this system is that the top block is going to accelerate a lot faster than the bottom block, and it's going to pull away like so. Conveniently, the top block's a lot smaller, so that's going to help us with that. So since there is slippage occurring, we can no longer use Fs max, and we need to resolve the entire problem using Fk, or kinetic friction. It's not too complicated for us to just replace 0.6 in our equation with 0.4, which is equal to mu k. Alright, now the force of friction is no longer 58.8, and it's no longer Fs max, it's just Fk. Fk is equal to 39.2 newtons if you solve that. And again, Fk acts backwards on m2, slowing it down, and Fk acts forward on m1, giving it its acceleration in the leftwards direction, 39.2. So again, sum of forces in the y from m1 we don't care about. Sum of forces in the x is going to be equal to Fk. For simplicity, this is 39.2 newtons left. So the acceleration of the two objects both change. The net force on the top object is now 60.8 newtons forward. So it's about 100 minus 39. And the acceleration of the top block A2 is equal to 6.08 meters per second squared. For the bottom block, the net force is 39.2 newtons leftwards or forwards, so the acceleration of m1 is going to be 0.98 meters per second squared. Just as we expected, the top block accelerates more and faster than the bottom block. There's slippage occurring, so we use kinetic friction, and these are the accelerations we're left with. Good luck on your final midterm. Feel free to email me if you have any more questions, and I'll see you guys hopefully on Sunday for the review session.